Welcome. In this video, we will be taking a look at a lesson from present value and capital value in 3.7. And let's take a look at the lesson objectives. We have two of them. The first is we want to leverage present value to compare investment strategies. And then a second lesson objective is finding and interpreting the capital value of an income stream. So we'll try to do both of those in this video. So let's start with the idea of continuous income streams. We'll read the definition and then we'll walk through the components of this calculation. So suppose money can earn an annual interest rate of R, compounded continuously, and let f of t be a continuous income function in dollars per year that applies between year 0 and year capital T. So the present value of that income stream is going to be given by an integral from 0 to T, and that capital T is really what we maybe call the term of the present value calculation. That's how long we're going to get that income stream. Inside the integral, we'll have the capital F of T function. That's the income stream that we want. This F of T is generally going to be a constant income each year, but it could be a variable income, maybe a linear function at most, multiplied by the e to the RT. That's really the compounding bit. This is very similar to compound interest for a future value, calculating a future value, but notice that there's a negative in that exponent. So this calculation is actually bringing all of these income stream payments to the present value and considering their present value at time 0. In other words, present value here we could think of as the equivalent lump sum payment to the income payouts. So if we took all of the income payouts that are given to us throughout this time 0 to T, the present value of those income payments over time is equivalent to a lump sum that we would get at the beginning. So the present value is really an equivalent lump sum that would be equivalent to the money in the future that our income stream payments will provide us. So let's take a look and see if we can use this expression to make some comparisons, and we'll walk through at least one of these calculations in depth, and then we'll kind of walk over the last two in a little less detail. So in this first example, we're going to do the comparison of a couple income streams or a couple investments. So we want to compare the following retirement payouts, and we want to rank each plan in terms of present value from least to greatest. So the present value really is a good way to rank how much each of these retirement plans is really worth. So it's the equivalent lump sum payment today that those three would be worth. So let's walk through part A, and we'll consider receiving $40,000 per year for 25 years. And we'll assume that's common interest rate of 5%. So if we consider each of these in terms of the variables, the $40,000 here, that's really our income stream. We'll call that the F of T function. That's constant right now, so it doesn't depend on time, but that is the income stream itself. The 25 years is going to be that capital T. That's the term of that investment. So that's the capital T. And we know that the interest rate R here is fixed at 5%. Realistically, the interest rate will ebb and flow, but for simplicity's sake here, we'll set it at 5%. So we want to take that as 0.05 as a decimal. And those are the only three components that we'll actually need to find present value. So let's go ahead and take a look at the integral that we're going to create. So we have present value. It's going to be equal to an integral from year 0 to year 25. The income stream is going to be $40,000 times the e raised to the negative 0.05 t dt. So one thing that we can kind of imagine this integral doing is it's really pulling all these payments back to time 0 and kind of adding up all their equivalent present values together to get a full present value of the full income stream. So let's take a look at actually evaluating this integral. Notice that we do have a constant value out in front here, and so we'll just kind of leave that for right now. The only variable in our integral here is that exponent with the negative 0.05t. So let's go ahead and consider how would we take an antiderivative of an exponential function. Well, if we consider the antiderivative of that exponential, we're really just going to have to rewrite the exponential and divide by the derivative of that exponent. So the constant value here will stay along, so that's 40,000, that's a constant. And that exponential here we can say is going to be rewritten and we would have to divide by the derivative of the exponent instead of multiplying by the derivative of that exponent like we would with the derivative. So this would be negative 0.05, and that would be the antiderivative of that function inside our integral. Now the only thing left to do here is going to be taking this quantity and evaluating it from our year 0 to year 25. Now, if we do this, we could punch this into our calculator, and if we do so with this evaluation is going to give us a sum, and I'll just round to the nearest dollar here. This is going to be in dollars, $570,796. So $570,796. That would be the present value, or the equivalent lump sum that would be equivalent to all of these payouts over the next 25 years. So you could say if you had this amount of money, this $570,000 in the bank right now and could get 5% interest, that would be equivalent to getting these current payouts of $40,000 for the next 25 years. So let's go ahead and just compare with the other two here, and the antiderivatives here are going to be very similar, so I'll just kind of set this problem up and give our solution. So the next present value for the income stream we want to consider is for a $50,000 payout over 19 years. So again, we'll go from 0 to 19 this time. That's the payout term. We have $50,000 as our income, and then our interest rate is the same. So notice that in the integral here, the antiderivative will be equivalent other than this constant right here. So that 40,000 is really just going to be turning into a 50,000, but otherwise the antiderivative here in this problem would be the same every single time for A, B, and C. So if you considered the integral here, and that present value, we'll just give that out. It's going to be a very similar calculation. This would be ending as 613,259. So notice that this income stream here is a bit larger. Again, this would mean that the $50,000 payouts for 19 years is actually worth more than our $40,000 payments at 25 years, or for 25 years. So even though the amount of years went down, it didn't go down enough to compensate for that $10,000 increase in income each year. So right now, B is now in the lead for the most valuable income stream. Let's go ahead and set up that last one. The present value for the last one would be an income stream over 14 years, so 0 to 14, with an income of $60,000, and then same interest rate, DT. If we calculate this one, again, in a very similar fashion, we would find that this income stream is $604,098 if we round to the nearest dollar. So $604,098. So if we compare all of these across the board, we'll notice that, well, what's the largest? Well, the largest is actually part B, followed up by part C, and then the actual income stream for the longest time, part A, is actually worth the least amount of money. So if we wanted to rank these in terms of value from least to greatest, well, the least would be, calculation on part A. The middle value would be part C, and then the greatest would be part B. Wanted to rank those. All right. So it's really important, again, just to get the idea that what is present value? Well, present value is, again, the equivalent lump sum to the income stream payments. That's simply what the present value is representing. So it's a great way to compare investment strategies with different years and different payouts, and even sometimes different interest rates. Okay, let's go ahead and take a look at our second section here and consider a few questions concerning our parameters. So the first question says, what happens to present value when the interest rate increases and all other parameters are held constant? So this answer for this is actually a little counterintuitive. As the interest rate increases, the present value of an income stream actually will decrease. So let's just write that out and then we'll talk about why. So as the interest rate increases, the present value of an income stream will decrease. Now, the reason why this is true is consider that if we have a higher interest rate, that means that there needs to be less money at the start, or what we'd call present value, to reach a given future value. So the larger the interest rate, the less I have to accumulate at the start, which we would call present value, to get to whatever my goal investment amount is. So the higher the interest rate, the lower the equivalent present value or the lump sum would be to a given income stream. So the second question we can consider is what happens to present value when the term or the time, that big T, decreases and all other parameters are held constant? Well, if the time is shorter, that means that we really just get less payments. So decrease in time means less payments or less payouts. And if there's less payouts, that means, well, the actual value of the income stream is going down. Therefore, present value is also going down. So we could say as time or the term length decreases, the present value of the income stream decreases. Now, that solution is probably a little bit more intuitive to us since there's less payments available to accumulate. That means the actual value of that present income stream is also less. So I think that one might be a little bit easier to understand. So let's go ahead and continue working through and take a look at our second objective in capital value. Now, capital value is a little bit different, but it's playing kind of the same idea with this income stream. So let's read the definition and look at some problems. So the capital value of an income stream represents the amount of money that must be invested to earn that income stream in perpetuity or forever. So the capital value of an income stream is given by the expression, we'll call it CV. It's the integral from 0 to infinity of our capital F of t e to the negative rt dt. So instead of having a fixed amount of years that we're getting this income stream, we're actually going to get this annual income stream in perpetuity, forever. So the capital value, in other words, when invested, will earn annual interest equal to that income stream. That's another way to consider it. That we'll be able to continually just live off, in other words, the interest that this account creates and never deplete our income. So let's take a look at a couple questions here. And the first one will kind of go into good detail about how to represent this through the integral form, and then I'll actually give you guys a second way to calculate these capital value problems in the second example. So the first one says, how much money must Jeremy have in his retirement portfolio to earn a payout of $60,000 a year, and we'll assume the market is giving a 6% annual return. Okay, so in other words, we want to know, well, what is that capital value that we can actually earn this income forever? Okay. So let's go ahead and consider how to set this up. The CV, or the capital value of this income stream from 0 to infinity, we'll want to take a look at. And we know that our income stream that we want to have is $60,000. And we know that we're getting 6% interest. Okay, so this was the integral that I actually want to solve. Now, we haven't seen integrals of this type yet, so we'll have to walk through and consider, well, how do we deal with that upper bound of infinity? So we'll do that in just a moment. Let's go ahead and put this to a notes page a little bit larger so we can walk through this a little bit more in detail. So in this income stream, we'll actually want to change these up. So our term really now is infinity, right? So we want to be able to get this income stream forever. The income stream that we actually desire to get here is going to be 60,000. And then our interest rate, R, we said was going to be 6%. So let's go ahead and consider setting that up one more time. So the CV, the capital value from 0 to infinity of $60,000 times e to the negative 0.06 t dt. So that's where we left off with our problem. So since we have an upper bound of infinity, we have to kind of deal with that in a little bit different fashion than a constant. So since we can't evaluate an integral at infinity, one tactic that we're going to use, and we'll do this in the next lesson as well, is we're going to take a limit as that endpoint approaches infinity. So what I can rewrite this as is we can say it's the limit as, we'll call this our b endpoint, goes to infinity of the integral from 0 to b of this expression 60,000 e to the negative 0.06 t dt. So now we have an integral from 0 to b that we can evaluate, and then we'll take a look at the limit at the very end. So let's go ahead and consider first the integral itself. So we'll keep this limit on the end. And we'll consider, well, how do we take the antiderivative of this function sitting in here? Well, we can rewrite this as just 60,000. That's a constant. And then we have e raised to the negative 0.06 t. And to take that antiderivative, I just have to divide by the derivative of that exponent for that exponential. So we divide by negative 0.06. And we're going to take this value and evaluate that function at b and at 0. Now, if you notice here, we can do some simplification with that 0.06 and 60,000. And I'd like to do that here. If we move this decimal 2 places to the right, we'll move this decimal also 2 places to the right. So we'll have 2 zeros to add there. And we can also consider 6, and 6 will cancel. So a couple cancellations there, and moving our decimal give us kind of a nice result here. We have on the outside here, we'll do the limit again. B goes to infinity. And here we'll have 1 million left over. So we have 1, 2, 3, 4, 5, 6 zeros when all added up there. And again, notice that this is negative, so we'll kind of tack that negative into the numerator. And we have e raised to the negative 0.06t, evaluated at b and 0. So a little bit cleaner way to view that expression just by looking at those constants. Now let's go ahead and evaluate our integral, and then we'll take a look at the limit. So we still have that limit as b goes to infinity. We'll first evaluate at b. So that will be negative 0.06 times b minus, we'll have negative 1 million times e raised to 0 times negative 0.6. 0.6 is going to be just 0. And now we can go ahead and let's just consider our limit as we walk across this and what this would be. Well, if b is going to infinity, if b is getting very, very large, well, notice the first time b comes up is right here in this exponent. And that's a negative exponential. So as the negative exponential, as the input increases, our negative exponential kind of looks like this. That negative exponential, e raised to the negative x, will decrease. And where is it decreasing to? Well, it's actually just decreasing down to 0. So as b gets very, very large in that first term actually goes to 0. So that first term goes to 0 here. And what about our second term? Well, the second term doesn't have any b variables. It's just constant. Notice e to the 0 is just 1. And we have a double negative here. Negative plus times a negative is just going to be a positive. And we just have 1 million left over. So this actually gives us our result. What is our capital value here? It's just going to be $1 million. This is the capital value of that income stream. So in other words, this tells us that if we had $1 million in an investment account that can earn 6% interest, we could live off of that and take $60,000 a year off of that account and live on that $60,000 and never touch the principal of this $1 million. So that's pretty cool to figure that out. Now, this is a pretty large sum, but the math works the same for larger or smaller values. So $1 million there is our present value. I'll just kind of note that. And we'll come back to this in just a moment to kind of test out our second method as well. We'll come back to that first example. Now let's go through these last two, and I'll give you guys again a second method maybe to figure this out. So how much money must Dominique have in her retirement portfolio to earn a payout of $75,000 a year? Assume the market is giving 8% annual interest. Okay, so let's just think of this in terms of just the interest that we're getting. Okay, so if I had, let's just say, present value or capital value here is some value. Once I get that capital value, what I really want to do is I want to be able to take 8% of that capital value of this account, and I want that to be my payout every year, right? Because if I'm only taking the interest, which would be 8% of my total, I want that to be $75,000. So to be able to solve for this capital value, I can actually do just a simple multiplication and division problem. So I really just want to know what is 8% of my capital value. So 8% of my capital value should be equal to my payout. And that works for any problem that we work through in this. So my interest rate or my interest rate percentage times my capital value has to be equal to my payout to make this work exactly. So what do we know? We know we have 8%, so that would be 0.08. My capital value, I don't know, but of would be multiplication, capital value. And my payout, I do know, that's 75,000. So what I can do here to solve for my capital value is I can simply divide by 0.08. So I get 75,000 divide by 0.08. And when I do so, I get a value of $937,500. And that would be the capital value or the equivalent lump sum that I can take 8% annual interest and just live off that interest and never touch that principal. And I could earn $75,000 with that 8% each year. Now, we could have done the same thing with our Part A, or our first example up here, and we can just show that for a moment. We know that in this case, we had 6% interest, or what we'd say is 0.06, 6% of my capital value has to be equal to $60,000. And if we divide by 0.06 in this case, capital value, $60,000, 0.06, this actually gives us $1 million as well, if we move that decimal and reduce. So this might be a little bit easier to figure out, but you do have to kind of know exactly what we're meaning by present value or capital value here to figure it out this way. So we can work this problem the opposite way as well, and that's what we'll finish up on in this last example. And it says, what is the maximum perpetual income stream that Jackie can receive from an account worth $700,000 and assume the market is giving 7% annual return? Okay, so in other words, what's the maximum that I can actually pull out of this account each year so that I can earn an income stream every year in perpetuity at the 7% annual interest rate? So it's really kind of asking the question in reverse. It's saying, I know the present value or the capital value of my income stream, that's $700,000, but how much can I actually pull from that? Well, in this case, I can only pull my interest rate out. And so what can I pull are the income stream payments. My payout, again, has to be equal to my capital value times my interest rate. And I know both of those items. So what's my capital value? It's the 700,000. And I want to know, well, what's 7% of that? That's the maximum I can actually take out of that account, because that's what I'm earning each year, to never actually touch that $700,000 principal. And if we multiply those two values out, we can get that as $49,000 if we multiply those two. So this is the maximum annual payout that we can earn from $700,000 at 7% interest to continue to get that payment every year in perpetuity. So that would be our solution there. All right. So I hope this video is helpful introduction to our present value and our capital value. We will do a few more of these types of examples in our next lesson after we go through our supply and demand. So go ahead and make sure you take a look at that video as well. if you are interested in more of those examples. So thanks for your time, and I'll see you in the next one.